So today I'd like to look at other ways of studying charge. So we've already looked at forces and fields, and we saw that there was a big limitation to these. So let me give a quick summary. When I have two charges, both positive, both negative, or one of each, doesn't matter, we can find the electric force. We could then take the electric force, plug it in, and find the acceleration of this charge. Alternatively, we could find the field created by the green charge, use it to find the force on the blue charge, and plug it in to get our acceleration. Either way, we get the same answer, and either way, that acceleration is not that useful. We talked about why it was not useful, and that is as soon as this object starts to accelerate, it will move further from the other charge. As it moves farther from the other charge, the force, the field, and the acceleration all diminish. So that acceleration does not last more than a nanosecond. Okay, so what you should realize is that this is a great way of finding forces and acceleration, but without a knowledge of calculus, we can't really use it for that many things. So we have other ways of studying the motion of the charge. And that other way relies on the idea of energy. So we've learned energy many times throughout the last 2 years. This is a new approach to energy. So we're going to look at potential energy, stored energy between two charges. So we have these two charges that are going to repel each other. If we're holding them in place, it's like holding a compressed spring. There is energy in there that is just begging to be released. So when we let go of this charge is going to fly away. We're going to assume that this charge is held in place. All right? So we have stored energy. Here's how we find our stored energy. It looks just like the force electric formula, but you'll notice that radius is not squared. The other way it's different is that with potential energy, it is not a vector. It does not have a direction. It just has a magnitude. So you calculate the potential energy of the two particles. Then you do it again, but at a new location. So if I wanted to find how fast is the particle moving when it reaches a distance of, let's say, 30 centimeters, I do the same formula I did originally again. I get the potential energy at the beginning, the potential energy at the end. I subtract the two potential energies, and that tells us how much potential energy I lost. That lost potential turns into kinetic. The kinetic can then be used to easily find the speed. This is so much better than using forces because we don't have to worry about the fact that the acceleration is changing continually. We just find the energy at the beginning, the energy at the end, and subtract. We can also attack it with another concept similar to field, and that's a concept you've heard of before, but not in this context. And that concept is the concept of voltage. Okay, so we find the voltage at a certain location. It's given by this formula. Notice that there is only one R, and notice there's only one Q. So this charge is creating a voltage in space. That voltage depends on how strong the charge is and how far away we are. We can then find the voltage at another location and see how much the voltage changed by. We then put the change in voltage in here, multiply by the amount of charge that's moving from place to place, and we could find the change in potential energy. We could then use that to find kinetic energy because it will be the same value. Okay, and then we could use that to find velocity. So two different approaches give us the same net result. You could either start with energy directly, or you could start with voltage and then calculate energy. Either way, it bypasses the inconvenience of having a force that is changing continually. Okay, so I want to summarize. We have four big terms in electrostatics. Force and field we learned last year. Energy and voltage we just talked about. We'll be practicing these ideas as we go forward. Okay, here's how these four formulas are linked together. So we have electric force, electric field, electric energy, and voltage. Notice, force has the most things. 2 charges, radius squared. In order to have a force, you need 2 objects. Field, we only need 1 object to create a field. We need another object to field a field, but only 1 to create it. Notice it's based on radius squared, so if you go twice as far, it gets 1/4 as strong. Over here, you'll notice that potential energy needs 2 charges. If we have stored energy, we need to have 2 charges. We can't just have 1 charge that has energy stored with nothing. Okay, so it's stored in the system of the 2 charges. Notice that it is not based on radius squared, but simply radius. Notice that voltage is missing a charge and it's missing a radius. A voltage is like a field in that an object creates a voltage. Another charge would be needed to experience the voltage, but only 1 is required to create it. Okay, it's based on radius and not radius squared, so if you go twice as far, you get half the voltage. Notice there are 4 other equations that link the formulas together. So we can take the electric field, multiply by a second charge, and figure out force. We can take the change in voltage, multiply by a charge, and get our energy. We can do voltage equals electric field times distance, and we can do work, which is energy I added to an object, by doing the force times the distance. Notice how it works out. If you take force and times distance, you get rid of one of your R's. Boom, it's gone. Down here, if we take electric field and multiply by distance, we get rid of one of the R's. That's why our voltage has only the 1 R, and that's why the potential energy just has R and not R squared. Okay, the way it works here is you'll notice if you take your electric field and multiply by another Q, you now have this formula. And if we take the voltage and multiply by another Q, we now get this formula. So 8 different formulas, 4 on the corners, applied directly. The linking formulas can apply in almost all cases, okay, to help join the different formulas together.